No, what's the title of your talk?
One. Do you want to put one? Okay, we're ready to start the final session and final talk of the conference. Everyone get seated. Get comfortable. Okay, so the final speaker is the guest of honor of the conference, Professor Murty from Queen's University, and he will speak on a very descriptive title, Some Research Problems in Number Theory, Part 1.
Well, thank you. Thank you very much. Firstly, it's customary that the last speaker of any conference has the distinct honor of thanking the organizing committee for setting up a wonderful conference. So let's thank them all. They certainly did a lot of work and everything went flawless. The title of my talk is Some Research Problems in Number Theory. I got the idea from a paper of Erdős. So it's sufficiently vague that you can, prepare your talk during the talk. Let me begin with a very elementary remark.
Ram, do you offer prices for solutions?
No, I'm not that rich. But in your case, I might make an exception. So
yeah, a bottle of beer would do the job.
Right. So let me begin with a very elementary remark. In fact, I think I first stumbled on this in a book on elementary number theory by Vinogradov. And the idea is very simple. If P is a prime congruent to 5 mod 8, then 2 is a quadratic non-residue, right? Everybody knows that. Mod P. Good. So 2 is not a square, mod P. Now, if P minus 1 is 4 times a prime, Q is a prime, then P is, of course, Q is an odd prime, let's say odd prime, and an odd number is of the form 2k plus 1, so this P is of the form 8k plus 5. So for such a prime, 2 is a non-residue, and what is the order of 2 mod P? Well, it can't be a square, so the order has to divide, 4 has to divide the order, and you can't have, is this okay? Can I write here or is it in the shadow? Up to half, okay, so up there, okay. So what we have is we have to check if 2 to the P minus 1 over Q is congruent to 1 mod P. So if 2 to the P minus 1 over Q is congruent to 1 mod P, i.e., what is P minus 1 over Q? It's 2 to the 4. That's 16 squared, and it's congruent to 1 mod P. This is the only obstruction. So prime divisors of 2 to the 4 minus 1 are the only obstruction. So if P is certainly bigger than 2 to the 4, then 2 is a primitive root mod P. It's bigger than, yeah, even 5 is good enough, yes. But at least this is certainly the case. So in other words, this elementary exercise, which is really behind my early work on proto-root conjecture, has to do with the fact that if you can sieve p minus 1 correctly and control the number of prime factors, you actually can get somewhere with finding generators. So this is the basis of the idea then is to apply a lower bound sieve to control the prime factors of p minus 1. And sufficient technology is available that one could do this very well. The most notable tool is the Bombiri-Vinogradov theorem. Combined with the Ivanich form of the lower bound sieve, gives rise to eventually the result that Sunil had mentioned in his talk, that if you take 3 mutually co-prime numbers, one of them is a primitive root mod p for infinitely many primes p. So this is basically, so starting from a very elementary and very basic result, one can use it as a muse to ponder deeper and get some non-trivial things. So never discount simple ideas just because they're so simple. What I'd like to talk about is what can be done further. One of the most spectacular results of the 21st century is, of course, Yitang Zhang's breakthrough result that bounded gaps between prime numbers. Now, so that's certainly a big Yitang Zhang. And when Yitang Zhang actually wrote his paper, the method was quite complicated, pushing the Bombiri-Vinogradov theorem beyond the exponent 1/2, but for smooth moduli. This was the big idea. And I think that there's still many ideas in that paper that have not been harnessed, but this has been simplified later by Maynard and Tao and the polymath group. And so what we have now is something like if a set script A consisting of A1 to AK is admissible, I'll tell you what that means in a second, admissible, then admissible and K is sufficiently large, then at least one of n plus A1, n plus AK is prime. The definition of admissibility is that the image of the set A mod P, the cardinality of this should be strictly less than P for all primes P. So that's a necessary condition for representability by primes, and it turns out it should be sufficient. That's the conjecture for any admissible set. And the interesting thing is that if you can vary this a little bit, the same method, the Maynard-Tao method, as I'd like to call it, isn't so particular about the use of the Bomberi-Vinogradov theorem that you need an exponent bigger than a half. Any exponent which is positive will work to give some sort of bounded gaps result. So the beauty of the Maynard-Tau method is that they eliminated the technicalities of the sieve, the Bomberi-Vinogradov theorem that you need. Any level of distribution which is positive works. So that means that one could impose, you want these to be primes, but you may want them to be primes whose Artin symbol is of a specific type in some fixed number field. You may want to impose that extra condition. And if you want to impose that extra condition, all you need is a Bomberi-Vinogradov theorem with a positive level of distribution. And Kumar and I, in 1987, I believe, proved what's called the variant of the Bomberi-Vinogradov theorem for number fields. Which allows to get the result that n plus a1, I forgot to say at least two of here, right? At least two. At least two of these, n plus a1 to n plus ak, are prime and have a specified splitting type in a given number field. So this comes out of the method. You can specify any Artin symbol that you want, yeah. So that's the beauty of the Maynard-Tau method. The intricacy of that sieving exponent has been eliminated, as long as it's a positive exponent. And so in my opinion, perhaps this result can be improved, and maybe one can tweak the numbers. The numbers, of course, can be tweaked, yeah. Now, if in a recent paper of Peter Moret, I was rather shocked to hear that he made a statement which, on clarification, turned out to be not quite correct. Anyway, one can modify the method, so modify the method to show that a1 n plus 1, a2 n plus 1, ak n plus 1, that at least two of these numbers are prime. So here, the Maynard-Tau method can be modified to show this result. Instead of looking at n plus a1, n plus ak, you can look at a1 n plus 1, a2 n plus 1, a1. The reason for this is because now, if these are primes, you have some sort of control over p minus 1. At least you know something about the AI. But the research problem that I'm alluding to in the title is can we make n prime and require only one of these, and require only one instead of two of a1 n plus 1, ak n plus 1 prime. Now, if we can do this, a nice consequence to the Artin primitive root conjecture is that given a number, let's say a or something, you want to make primitive root, the index is bounded. You can make the, yeah? Pardon me? Yeah, exactly like this, exactly, yeah. So a consequence of this is, if you could do this, this would be nice to see. Since the technology seems to be moving in that direction, maybe one more new idea is needed in the Maynard-Tau method in order to get this result. The consequence there would exist infinitely many primes, P such that the index of A is bounded for any given, let's say 2 if you want. Let's say 2. This, you can get that. So that's one of the nice consequences. Did you have a question? Oh, sorry. The index is bounded. Sorry. Yeah, you're right. Some constancy. Yeah, thanks. Yeah. So that's one of the problems that I was thinking of putting in front of you in this context. Another problem has to do with something that's been bandied about for a long time, and this has to do with the parity problem. So let me just say a few words about that. And the first person to highlight this problem in sieve theory was Selberg in his 1946 paper. He was trying to say that there's an inherent obstruction. Sieve theory is not going to probably give you infinitude of twin primes. It will not give you, of this anything like this, where we're primes and shifted primes. So the twin prime problem and this problem, of course, are all kind of connected. So Selberg's remark is sieve theory is unable to distinguish numbers with an even number of prime factors from numbers with an odd number of prime factors. What is it? No, no, I don't. No, you're thinking of the Chen-Ivanich switching argument. Selberg inequality? It could, yeah, maybe there's a little bit, but it's not, yeah, it's not clear. Anyway, yeah. So this is what he makes as a comment. And then this has been referred to as the parity problem, but no problem has really been formulated per se. And I remember my colleague Francesco Cialarussi once asked me during coffee time that Sarnak had made a comment that the parity problem and the twin prime problem are connected, and he wanted me to explain to him what did he mean by this. So at that time I had a PhD student, Aksha Watwani, who spoke in the morning, and I told her, let's try to put something on the record and see if we can make a very clear statement as to how the parity problem and the twin prime problems are connected. So we wrote a paper which you can refer to. It was published in the Journal of Number Theory. And so let me try to explain this. Now, in the course of time, I think I have 2 or 3 other ways of explaining the parity problem, which haven't been worked out yet, but are worth working out, which probably will also elucidate this issue. It will not actually solve anything, but I think that it'll establish an interesting connection between this parity problem and prime shifted primes. The idea. So let me recall. So let me say by self and Aksha. We wrote a paper called Twin Primes in the Parity Problem. So the question is, okay, Selberg is saying sieve theory is not going to solve the parity, the shifted prime problem. What else do you need beyond sieve theory in order to solve it? So in order to say something intelligent, so let me kind of refresh your memories about the twin prime problem. So recall this von Mangold function. It's log p if n is a prime power and 0 otherwise. So this is p's prime. This von Mangold function is an interesting, important function. The prime number theorem is the assertion that summation n less than x lambda of n is asymptotic to x. That's the prime number theorem. The twin prime or shifted prime problem a la Hardy and Littlewood is the assertion that if I have some shift h is not 0, if I have that, this should be also asymptotic to some singular series times x as x goes to infinity. This is the conjecture. This is conjecture. So you may say Hardy-Littlewood conjecture. So this is still the open problem. We don't know anything about it. Now, how can I formulate the parity problem? Can one make it very precise? So the parity problem is somehow the assertion that's the way we want to make the statement of the parity problem. Parity problem, somehow the number of primes when I shift that are with the even number, an odd number, we formulate it like this. So this is a conjecture. In some sense, this conjecture is very reminiscent of another conjecture attributed usually to Chawla. So it's a Chawla style conjecture. So this is a kind of Chawla style, or at least we say Chawla's conjecture suggests. So we kind of say this is Chawla's conjecture in some sense. Mu is a Mobius function. Thank you. Yeah. where mu is the Mobius function. So let me just define the Mobius function. 1 if n equals 1, minus 1 to the k if n is a product of k distinct prime factors. Distinct. And 0 otherwise. So in other words, the Mobius function is plus 1 if it has an even number of distinct prime factors, minus 1 if it has an odd number, and it's 0 if it has a repeated prime factor. You have a question? No, he didn't, Paul. Yeah, yeah. He had the Mobius functions. He had mu of n plus h. Yeah. Oh, because lambda of n is already prime, right? Yeah, mu of n is just minus 1. You want to talk about the shifts. So this is the conjecture that seems to be inspired by Chawla in this context. And so call this the Chawla parity conjecture. Yeah. And you could explain what happens with this particular man times or something like that? Yeah. I think one could easily make an analogous conjecture for other shifts, linear shifts. Yeah. Absolutely. I mean, so the question is that when we have, following the Polya principle, when you have an unsolved problem, you may have a hierarchy of unsolved problems in between. So let's formulate them and see which, if we can get somewhere with some of these things. And that's the process for I suppose, some sort of research. So I mean, I have no idea what Sarnak had in mind when he told my colleague that the parity problem implies infinitude of twin primes. But it looks to me as if some form of Elliot-Halberstam conjecture is needed. So let me try to explain the connection of the Elliot-Halberstam conjecture and a version of the shifted prime conjecture. So it seems reasonable to formulate, how many T's? Elliot has 2 T's. Halberstam conjecture. Fix epsilon positive. And look at then for any A, we have so these are primes in arithmetic progressions. So this is what's called the Elliot-Halberstam conjecture. If I replace 1 minus epsilon with a half minus epsilon, that's the Bombiri-Vinogradov theorem. And so the Elliot-Halberstam conjecture is predicting that we can really go very far, and it's a result of Granville and Friedlander that we can't go really too far, like x over powers of log is out of the question. But I'm not so sure what the right limit is between x to the 1 minus epsilon x over arbitrary powers of log. There might be some intermediate range where we can go. I would wager the guess it's x, x to the 1 over log x, 1 over 1 minus log. I would wager that guess. And if that's the case, then one would have a very simple proof that the parity problem as formulated there, plus the extended Elliot-Halberstam implies twin primes, if you had that extra piece. So the point is, what is the allowable limit in the Elliot-Halberstam conjecture beyond things like this? And if you're allowed to go, if you're allowed to replace this, this x to the minus epsilon by x to the 1 over log x, then you have a very simple proof connecting parity problems implies that. So parity, that conjecture, Chow-law conjecture, does imply this asymptotic formula. So now, let me just say what we do in this paper. How am I doing for time? Okay. Huh? Oh, okay. Well, maybe I'll take only about 10. So let's see. So we'll make the following. The Mobius Elliot-Halberstam conjecture is there exists an eta positive such that for any A we have summation q less than or equal to x to the eta max. Now you may think that, what is all this max business? Why couldn't you just stated it for x? It turns out this is a more convenient version of applicable in sieve theory, this version. So in the same style here, we will take n less than y, n congruent to A mod q, lambda of n, mu of n plus h. So that's the sum we're really interested in, but I'd like to know what's going on in arithmetic progressions, minus the expected value, which is probably small, but it's better to state it in this way, simply because you don't want to make any new hypothesis on how this sum behaves. This sum should be bounded by x over powers of log. So the theorem then is, the Mobius Elliot-Halberstam conjecture for any positive eta plus the Elliot-Halberstam conjecture implies the shifted prime conjecture, so implies summation lambda of n plus h, n less than or equal to x, is asymptotic to some singular series times x. The singular series is, I think, familiar to many of you. I forgot what it is. What is it? It's product P divides H, 1 plus 1 over P minus 1. Product P doesn't divide H, 1 minus 1 over P minus 1 squared. So it's a convergent series, but anyway, it's non-negative. So this implies that, in fact, let's see, we are a little bit bold in this thing. Pardon me? Yep. Yeah, the implied yeah. This, of course, yes, yeah. Yeah, if you have 0.001, that's good enough. Yeah, for any A. And if you have that, plus the Elliot-Halberstam, you can show twin primes. So it's this one extra thing that you somehow need. In fact, so we assume the Mobius Elliot-Halberstam and the Elliot-Halberstam conjecture. This implies this conjecture. In fact, it also implies, so under this extra hypothesis, the Elliot-Halberstam plus epsilon, the Elliot-Halberstam plus this Mobius Elliot-Halberstam in a tiny range will give you this, and it'll also give you the Chawla conjecture, of course. It gives you the Chawla conjecture, and in fact, once you assume though, these two turn out to be equivalent. These two turn out to be equivalent. In other words, the shifted prime problem conjecture and the Chawla conjecture turn out to be equivalent under the umbrella of the Elliot-Halberstam conjecture and the Mobius Elliot-Halberstam conjecture. So that's, in a sense, perhaps all I wanted to say. I just wanted to add a few more small remarks that it's a kind of a different theme. Variations on this theme. About 20 years ago, Peter Murty and Stefan Hagen, Murty and Stefan Hagen, they formulated what's called the two-variable Artin conjecture. Very interesting conjecture. Take given A and B co-prime. They were asking, are there infinitely many primes P such that the subgroup generated by A is contained in the subgroup generated by B mod P. The subgroup generated by A is contained in the subgroup generated by P mod P. Are there infinitely many such primes? And then they answered in their paper that assuming the generalized Riemann hypothesis implies that indeed the answer is yes, and the number of such primes is asymptotic to some constant, positive constant, times pi of x. So we have under the Riemann hypothesis this, and I just wanted to announce some recent work that I had published with two young colleagues of mine in India, who one of them just finished her PhD, and the other one is still, I think, working on her PhD with Purushottam, who's here. And this is joint work with Suhita Hazra and Jyotsna Sivaraman. And what we show is unconditionally, we eliminate the Riemann hypothesis. We have the number of such primes without the Riemann hypothesis is bigger than x log x over log x squared for any pair AB with AB coprime, and somehow at most one exception, which I don't want to explain exactly what this exception business is, but let me just say that the result is true most of the time without the Riemann hypothesis. So that's a nice result. Now this result is really a tour de force of the lower bound sieve. The techniques that were used in the classical Artin primitive root problem, in the 1 of the 2, 3, 5 result being a primitive root, that uses the lower bound sieve. Here now we're able to exploit the Bombiri-Friedlander-Ivanich extended theorem, which allows for an exponent of 4/7 with what's called the theory of well-factorable weights. And we're able to exploit that. And the two-variable nature allows a certain degree of freedom, which allows us to sneak in an extra modulus and tailor the whole thing and then add up over all the primes. So basically we fix a prime and play the game with each prime, and then we have an x over L times log x squared, and then we can sum over the L, 1 over L's, and get the extra log x. So this is an interesting result. It stands midway somehow between the positive density results, which are desirable but can only be obtained by using Riemann hypothesis, and the lower bound sieve results, which seem to give you only x over log x squared. At least we've pushed it a little bit further and got some intermediate results. So that's basically all I wanted to put in front of you, a plethora of problems, starting from a very elementary observation, very elementary question, how often 2 is a primitive root, and it opens up methodologies. And I think even this parity issue, this is not the final say. I believe that there are other ways of answering how is the parity problem connected to the twin prime problem question as a meta question, as a meta question in sieve theory. And I'm sure Henrik would probably have more things to say about this, but this is all I can say at the moment.